Okay, in this video we're going to look at higher order derivatives. We're going to look at some definitions, a physical application, and then some mathematical examples. So what do we mean by a higher order derivative? So in previous videos we've seen that a function given by f of x, its first derivative can be given by f prime of x, but differentiation can go higher than the first order. So for example, the first derivative of our f prime of x is equal to f prime prime of x. All throughout my videos I've used the notation f of x just to try and keep it the same throughout. However, a lot of you will probably have seen that there are a lot of other types of notation, such as y. Then if we want to find the change of y with respect to x, the first derivative is given with respect to x as dy by dx. And then in the same way, if we go the rate of change with respect to x of our dy by dx, we have d2y by dx squared. And this is our general notation. However, it can keep going. So f prime prime of x, if we took another derivative with respect to x, we'd be left with f prime 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 of x, and then further derivatives of f of x with respect to x are usually seen with a Roman numeral annotation. So we can keep going. The fifth derivative with respect to x, then the sixth derivative with respect to x, and so on and so on. And similarly, our d2y by dx squared notation can be taken further. d3y by dx cubed, d4y dx to the fourth power, and so on and so on. So that's a definition of higher order derivatives. But one physical example of higher order derivatives is the rate of change of position with respect to time. So for example, the rate of change of position with respect to time, if we call position x, is given by dx by dt, where t is time. And for this, a different type of notation is sometimes used. It's x dot, which is the Newtonian notation for a derivative with respect to time. And as it's the rate of change of position with respect to time, this is defined as the speed of an object, or its velocity along a certain path. And then if we take the next derivative, so dx dot with respect to time is given by x dot dot, which is the change of velocity with respect to time, which is known as the acceleration of an object. And these two are the most commonly seen in Newtonian mechanics. However, it goes even further. For example, the third derivative. If we take the derivative of acceleration with respect to time, it's x with 3 dots, and it's defined as a jerk of a system. So how acceleration changes with time. And these become increasingly harder and harder to measure. And then even further than that is the derivative of the jerk, which is the fourth derivative of x with respect to time, which is known as the jounce. sometimes snap. So this kind of thing is most often seen in the field of classical mechanics, but in these videos we're just studying the pure mathematical side of things for now. So let's look at a couple of mathematical examples. So in our first example, if we have, using the same notation as the previous videos, if we have f of x is equal to 3x to the fourth power plus the sine of 2x, we know using the sum rule that this is equal to the derivative of the first part plus the derivative of the second part. So this first part here, 3x to the fourth power, its derivative can be given using the power law as 12x reduced to the power by 1 to the third power. And then the derivative of the second part can be found using the chain rule, which was in the previous video. So the derivative of sine is cosine, and then we have to times by the derivative of what's inside the bracket, so times 2. So this is 12x cubed plus 2 cosine of 2x. So now that we've got the first derivative, we can take it even further using this definition here. So the second derivative, f prime prime of our function, again using the power rule, we can see that's quite simply 36x squared. And then we have 2 cosine of 2x. So the derivative of cosine is minus sine. So we're going to have minus sine of 2x. We're already multiplied by 2. You have to also multiply by the derivative of what's inside the bracket with respect to x. So we're going to have 2 times 2. So we're going to have 4. So that's equal to 36x squared minus 4 sine of 2x. And with trigonometric functions, we could keep going on forever and ever. So let's look at another example. So in this example, I'm going to switch the notation up just to increase familiarity. So in example 2, we have y equals 7x plus x e to the 2x. And using the rules in the previous videos, we know that dy by dx can be given by the derivative of 7x, which is 7, plus the derivative of x e to the 2x. So using the product rule, we know that we can take the derivative of this and leave the second part alone. So the derivative of x is just 1, so it'll just be e to the 2x, plus leave the first part alone and take the derivative of the second part. So the derivative of e to the 2x is going to be e to the 2x, and using the chain rule, we need to times by the derivative of what's in here, so times 2. So we're left with 7 plus e to the 2x plus 2x e to the 2x. So then if we want to take the second derivative of this function, we would have d2y by dx squared, which means the second derivative of y with respect to x. Then using the sum rule again, we have the derivative of 7, which is 0, plus the derivative of e to the 2x, which again using the chain rule is 2 e to the 2x, plus the derivative of 2x e to the 2x. So again, using the product rule, the derivative of 2x is 2, and we leave the second part alone, plus leave the first part alone, 2x multiplied by the derivative of the second part. And again, by using the chain rule, we know that that is 2 e to the 2x. So we're left with 4 e to the 2x plus 4x e to the 2x, which can be simplified by pulling out a 4 e to the 2x term, 1 plus x. So there we found the second derivative of a more difficult function. So to conclude, higher order derivatives are just further derivatives. All you need to do is repeat the process. And hopefully this video has helped you understand a bit more. If any part of it was confusing, such as how we use the chain rule, or the product rule, or the sum rule, then I would suggest going over and having a look at the videos I've produced on those. As always, if there are any questions, feel free to pop them in the comments box below. In the next video, we're going to begin a new topic, that's integral calculus, integration. See you there.